Hi everybody, welcome to lecture 14 of Electrical Engineering 331. In this lecture we will talk about causality, stability, and frequency response. So let's go ahead and jump right in. What we're going to do to begin with is consider problem 2.22 in your text. That problem says, determine whether or not each of the linear time invariant systems whose impulse responses are given are I, causal, and or II, BI, BO stable, which means bounded input, bounded output stable. Now, you should, if you have not already done so, you should look in section 2-6 of the text to get background material on these ideas about causality and BI-BO stability. But what we're going to talk about is how to work problems of this type concerning these concepts. So, let's first of all talk a little more about causality. As is described in section 2-6, a system is causal if and only if its impulse response, h of t, is a causal signal, which means that h of t is equal to 0 for all t less than 0. If that is true for a system, and only if that is true for a system, will the system be causal. And then for the second concept, BI-BO stability, we also have an if and only if condition governing that as well, and that is also discussed in section 2-6, and it says that a system is BI-BO stable if and only if its impulse response, h of t, is absolutely integrable, which means that if you integrate the absolute power, that's why they call it absolutely integrable, if you integrate the absolute value of the function from negative infinity to infinity, is that finite? If so, then the system is BI-BO stable. If not, then it is not BI-BO stable. So let's look at a few cases now and see how this goes. Okay, in the first case, we're looking at a system whose impulse response is e to the minus absolute value of t. And notice that we don't have any kind of a u of t multiplying that, so that means that this is the expression for all values of t. And right away we see that this system is not causal because h of t is not equal to 0 for all t less than 0. You know, if you plugged in, for instance, let's say you plug in t is -1, then the absolute value of -1 is 1, and so you would have h of -1 is equal to e to the -1, which certainly is not equal to 0. So we're finding, I mean, in fact, to be honest with you, h of t would not be equal to 0 for any value of t less than 0. So certainly this is not a causal signal. So now we move on to ask if it is BI-BO stable. Okay, remember that for BI-BO stability, what we want to do is to integrate the absolute value of h from negative infinity to infinity and see whether or not that is finite. So that's what we will do, is we'll integrate from negative infinity to infinity the absolute value of e to the negative absolute value of t. Now, this absolute value around the exponential function is really unnecessary because that's always going to be positive anyway in this case. So because we're only considering real values of t, so this is always going to be positive anyway. So we can drop those values, the absolute value signs. And now we have the integral from negative infinity to infinity of e to the negative absolute value of t dt. Now the best way to evaluate this integral is to break it up into an integral from negative infinity to 0 plus an integral from 0 to infinity. And you might say, well, why do that? Well, it's because the absolute value has a different expression when t is negative and when t is positive. If t is negative, then the absolute value of t is negative t. But on the other hand, if t is positive, the absolute value of t is just t. So that's why it's helpful to break up the region negative infinity to infinity into the negative region of t and positive region. Okay? Well, now, of course, negative of negative t up here is positive t. So this first term is just the integral from negative infinity to 0 of e to the positive t dt. The second term we can go ahead and integrate. We need a negative sign on the inside so that we'll have a form e to the u du. And when we put a negative on the inside, we'll also get a negative on the outside. So we have minus e to the u evaluated from 0 to infinity. Okay, and so now we come down to the next line and we see that this integral already has the form e to the u du, and so we just get e to the u from negative infinity to 0. Now for the other term, we bring down the negative sign. E to the negative infinity is 0, e to the negative 0 is 1, so we have 0 minus 1 there. And likewise, when we evaluate the first term, e to the 0 is 1, minus e to the negative infinity is 0. So we have 1 minus 0, and then this term becomes minus a minus 1, which is plus 1. So we have 1 minus 1 plus 1, which is 2, which is clearly a finite number. So this system is BI-BO stable. Again, it is not causal, but it is BI-BO stable. Okay, let's look at B on that problem. For part B of this problem, we're looking at a different impulse response. In this case, we have h of t is equal to, and this expression is a little bit complicated looking at first. You have one parenthetical term here, 1 minus absolute value of t. And then within the next parentheses, you have u of t plus 1 minus u of t minus 1. So at first, this may look a little bit complicated, and that's why I'm recommending that you graph the function. But once you graph it, I think you'll see that it's not hard at all. Okay, so this u of t plus 1 minus u of t minus 1, you know that for t less than negative 1, both of these terms are 0. So this function certainly cannot be, this function is certainly 0 for all t less than negative 1. Now for t between negative 1 and 1, this term is equal to 1 because the first step function is turned on. As soon as t exceeds negative 1, then this first term will become, at negative 1, it will have an argument of 0, and then if t is any bigger than negative 1, then the argument will be positive, and u of a positive number is going to be 1. So as soon as t exceeds negative 1, this term turns on and will be equal to 1. On the other hand, for this second term, it will turn on when t is equal to positive 1. As soon as t exceeds positive 1, then this is equal to 1. And then this term in parentheses becomes 1 minus 1, which is 0. So this parenthetical term here is equal to 0 for t less than negative 1, and it's equal to 0 for t greater than positive 1, or for t between negative 1 and 1, this is just equal to 1. So all we really have to do is concentrate between negative 1 and 1 and see what this is equal to between those values. And between those values, you can see that at negative 1, it would be 1 minus the absolute value of negative 1, or 1 minus 1 is 0. So it would be 0 here. But at 0, it would be 1 minus the absolute value of 0, which is 1 minus 0, which is 1. And then at 1, it would be 1 minus the absolute value of 1, which is 1 minus 1 or 0. So this is what the function looks like in between negative 1 and 1. And now this is the complete graph of the function f of t. So now that we have that, now that we have the picture, it's easy for us to finish this problem. Is this causal? Clearly it is not causal, because h of t is not equal to 0 for all values of t less than 0. Here we have these values of t less than 0 here, but we see that the corresponding values of h are not equal to 0. So this is not a causal function. And what about BIBO stability? Well, remember, to check that, what we have to do is to check whether or not h of t is absolutely integrable. So we look to see about this integral negative infinity to infinity of the absolute value of h of t dt. But this h of t is always positive, so we could take away the absolute value sign, and then the integral negative infinity to infinity of h of t dt is just the area under this curve, and that's a triangle, so the area under that curve is just 1/2 base times height, which is 1/2 times the base, which is 2, times the height, which is 1, so 1/2 times 2 times 1, which is 1. That's clearly a finite number, therefore h is indeed absolutely integrable, so this system is BIBO stable. And now let's look at one last case. What if h of t is equal to cosine of 2t u of t? Well, because of the presence of that u of t that's multiplying cosine of 2t, we know that h of t will be equal to 0 for all t less than 0. So this system is causal. Now let's check for BIBO stability. Well, if we integrate from negative infinity to infinity the absolute value of this function, well, the first thing we notice is, as I just said, the function is equal to 0 for all t less than 0. So we really don't have to integrate from negative infinity to infinity. It's sufficient to integrate from 0 to infinity, because the integral from negative infinity to 0 would be 0, because the function is 0 there. Now, let's see. Oh, and I've made one little mistake here, and so I want to go ahead and correct that. This is a graph down here, not of h of t, but of the absolute value of h of t. And I've graphed that because that, after all, is what we are integrating. So let me pause the video for just a moment and put absolute value signs around that h of t. Okay, so now the absolute value sign is there. And again, I'm plotting the absolute value of h of t because, after all, that's what I want to integrate. Okay, so when I plot the absolute value of h of t, I'll get a function that looks like this. And that pattern will continue on forever in the positive direction. Now, if you think about it for a moment, the integral will just be the area under all of these curves, but we keep adding more and more and more curves there, or more humps, whatever you want to call this. We will keep on adding more and more area forever and ever. So this is not absolutely integrable. The integral is not finite, and therefore this system is not BI-BO stable. So that gives us a few examples of determining whether or not systems are causal and whether or not systems are BI-BO stable. And in each case, that was based upon an analysis of the impulse response of the system. So this just once again, as we claimed before, the impulse response is really fundamental to the system, and we can see again an example of that right here. So the last thing we want to talk about in today's lecture is a concept called the frequency response, and we can begin to learn about that in problem 230 in your text. So suppose that a linear time invariant system is described by the LCCDE. That's linear constant coefficient differential equation. And here's the differential equation that describes the system. And we're going to assume that the input to this system is cosine of omega t. And I want to stress now, this is not cosine omega t times u of t, it is cosine of omega t. That exists for all time. So if we put in cosine omega t, if we put in that as the input to this system, what is y of t? Well, we haven't seen any problems like this before, and so we need to get a handle on how to solve something like that. And you will see a discussion in section 7, and what it says is the following. It says that when the input to an LTI system, described by an LCCDE, is a sinusoid, which means that it has a form of either sine or cosine of omega t plus alpha. By the way, it could also actually have a magnitude out here, like a sine or cosine, but we don't have to worry about that here. We can just say sine or cosine of omega t plus alpha. Then the output will be the magnitude of h of omega times the sine or cosine. And the way you should understand this is if you have the sine function up here in the input, then you have the sine in the output. On the other hand, if you have the cosine in the input, you'll have the cosine of the output. So whichever function you have up here, it'll be the same function down here. But notice what happens. The magnitude, instead of being 1, is equal to the magnitude of h of omega. And in here, the argument of the sinusoid is still omega t plus alpha, but now there's another term, which is the argument of h of omega. Here we're thinking of h of omega as being a complex number in polar form. So this is the magnitude of h of omega, and here's the phase of h of omega. And h of omega is the frequency response function, or is also called just simply the frequency response. So you can see that the frequency response is pretty important, because if we can find the frequency response, then we can easily find the response of the system to any sinusoidal input. All we have to do is to evaluate that complex number h of omega, and then plug in its phase here and its magnitude here. But how do we find h of omega? Well, there's a very useful input-output pair. Now, what we've given up here is certainly a useful input-output pair, but there's one that's even more useful than that, And that is the following. If x of t is equal to e to the j omega t, now keep in mind, this is a complex signal, because e to the j omega t is equal to cosine of omega t plus j sine of omega t. But if the input is equal to that, then the output is equal to h of omega times e to the j omega t. And that allows you to find h of omega. How? Well, just let's see. If we plug in, remember, this was our differential equation we're looking at. So what we're going to do is plug in this for y everywhere and plug in this for x. Now keep in mind, when we take the derivative with respect to time, it doesn't affect this h of omega. That just comes right outside of the derivative. And the derivative of e to the j omega t is just j omega. Each time we take a derivative, we'll get another j omega. So when we take the derivative twice, we will get j omega squared h of omega e to the j omega t. Then when we take the derivative once, we'll get a single j omega here. So 2 j omega times h of omega e to the j omega t. And then here's 7 times y, so 7 h of omega e to the j omega t. That's what we get on the left-hand side when we plug in this for y. And then on the right-hand side, when we plug in this for x, we just get, again, since we're taking derivative with respect to x, this 1 j omega will come out. So we have 5 times j omega e to the j omega t. And now, if we cancel e to the j omega t everywhere, see, that's the beauty of doing things this way, is everything has e to the j omega t in it, so we can just cancel it out on both sides of the equation, and we get this much simpler equation. And now factor out h of omega on the left-hand side, so you have h of omega times j omega squared plus 2j omega plus 7 is equal to 5j omega on the right-hand side. And therefore, there you have it, just that simple. H of omega is simply equal to 5j omega over j omega quantity squared plus 2j omega plus 7. And so now that we have the frequency response, and notice we have h as a function of omega, so we could find out the value of this function for any omega. But now we will be ready in our next lecture to come back up here to the question. We will be able to evaluate that at 2 radians per second and then find the y of t that corresponds to x of t equals cosine of 2t using this information right here for the input and output when the input and outputs are sinusoids. So we will do that next time. It's not complicated. However, we will have to remind ourselves a little bit of some complex arithmetic, because we will need to look at finding both the phase and the magnitude of a complex number. So if that's something you have not done in a while, you might want to review it, but we will cover it thoroughly in Lecture 15. So that concludes Lecture 14, and good luck.